Imagine the Sahara and the Antarctic in the same place. The place exists. It's called Kazakhstan. This single country is double the size of Western Europe, yet you could fit the entire population into London and New York with room to spare. Kazakhstan has only 15 people per square mile, and no wonder. It's one of the most extreme climates on Earth. For centuries, this is what a Kazakh building looked like. One fraction the size of this. The Pyramid of Peace is the showpiece of Astana, the world's newest and most remote capital. A 250-foot-high steel and glass monolith, harking back to the pyramids of ancient Egypt. It's so big, it houses a botanical garden, a museum, and an opera house. It's one of the boldest buildings on the planet. But what's boldest of all is, it shouldn't even be here.
Wherever you go throughout the world, you'll find engineers trying to find solutions to the world's building problems.
George Kaliris is a structural engineer hired by the building's celebrated architect, Norman Foster. Foster's projects are as big as they are daring. But this time, some thought Foster was going too far. No one had ever designed such a complex building in such an extreme environment. In summer, the thermometer soars past 105 degrees Fahrenheit. At night, it drops to 35 degrees, a swing of nearly 70 degrees in 12 hours. In winter, the plains are frozen for 5 months. The mercury can plunge to minus 50 degrees Fahrenheit. When 120-mile-an-hour winds blow in from the Arctic, the wind chill reaches minus 70 degrees, some of the coldest weather on Earth. Conditions like these make it hard to build a simple house, let alone a giant pyramid. The construction season in Kazakhstan lasts only 6 months.
In the winter, in Astana, it's very cold. Therefore, you can't really cast concrete during that time of the year. So we needed to have a solution in place where, we avoided that.
George devised an unorthodox solution. He set the pyramid's concrete foundation during the summer. Meanwhile, the entire upper structure was prefabricated in England in 1,000 triangular sections. By autumn, the pieces were trucked to Astana to be assembled.
Because we essentially designed this as a kit of parts, almost like a Lego system, still it can just come together as a series of pieces during winter, connect as required, and the building would be erected even though it's extremely cold outside.
Hard as it was, putting the Legos together was the easy part. Now George had to keep them from falling apart.
Now, one of the big issues we had here on the pyramid was how does this building tolerate the extreme temperature variances of plus or minus 4 degrees Celsius?
Even the most rigid buildings respond to extremes of temperature. They contract in the cold of winter and expand in the heat of summer. The pyramid is no different, but because of its sloping shape, all that expanding and contracting would spell disaster. The walls would snap and shatter.
We've been designing buildings many years now where, you know, they've been able to tolerate temperature changes. But the funny thing about this building is the geometry is such that it's different. It's had to breathe.
We've done that by allowing the building to sit on roller skates.
George did it by placing the pyramid's 40 columns on special interfaces known as slip bearings. Only 4 of the columns are nearly rigid. The other 36 can move in virtually any direction. The entire structure can move in and out like a giant lung.
This form of structure and how it's had to respond to the environment and so on is unique. And, you know, it's this problem solving which is intuitive for an engineer.
In September 2006, dignitaries from all over the world came to celebrate the pyramid's opening.
This is the first time I've seen the pyramid since I issued the drawings to allow this thing to be built. And actually, to be honest, I actually didn't think I'd see